Who thinks they have an answer? What are you coming up with, Ryan?
I got 29.
29. So 29 out of the 200 students have none of the courses. Okay. Josh, what do you? Forget about the actual question. You got hypnotized by the circles. Anybody else have an answer? Kevin. He's got 74. Logan?
68.
He's got 68. I don't think I've heard the right answer yet. Let's take a look. And this is why I suggested that you use a pencil. When you're looking at a Venn diagram problem, you don't start at the beginning. You start with the information that's going to give you the most information as far as all the sets go. So I would start with the 15. Where does the 15 go? Where should I place it? Where? In the middle. Does that make sense? If 15 students have geography, science, and art, they would go right in the middle. What you have to realize is that those 15 people are in all three sets. So we can't double and triple count them. For some reason, when people see sets like geography, science, art, they tend to think subconsciously that the set is just this section. The set for geography is this circle. The set for science is the entire circle. The set for art is the entire circle. So art already has 15 people in it. Geography already has 15 people in it. Science already has 15 people in it.
I got 70.
We'll see. Then I would move up a notch. I'd go to the next piece of information that involves more than one set. 31 people have science and art. Science and art overlap right here. Darken in this little football shape. What's the name of that guy on the...
Arnold.
What's the name on that cartoon?
Hey, Arnold.
Stewie? Is that his name?
Okay.
All right, this is Stewie Head. What show is that? Family Guy? How many people are already in the football? 15. We want a total of 31, so how many more people do we need? Now we have 31 people who are taking science and arts. Move up a notch. We just did 15. We just did 31. Now we're going to do 33. Look for the next Stewie Head. 33 have geography and art. We'll use blue for that. Geography and art would be this football shape right here. How many people are already in that football? 15. How many more do we need to get a total of 33? 18. We getting the hang of this? Then the other overlap would be geography and science. Geography and science is this shape right here. We need a total of 35. How many more people do we need? We need 20 more people right there. Now we move to the actual total within the sets. 60 have art. Art is this entire circle, which already has 18, 15, and 16 inside of it. 15 and 16 is 31. 31 and 18 is 49. How many more do I need to get 60? I need 11 more. When you're done, you should have 60 in art, 80 in science, 70 in geography. Move up to science. Science already has 15, 16, and then 20 inside. 31, 20, 51, how many more to get 80?
$29.
29. That takes care of science, and then I move on to geography. Geography is this circle, which already has 20, 15, and 18 already inside of it. 33, 20, that's 53. How much left to create 70, Kyle? 17. That's great. This is where Josh stopped. Now he's actually got to answer the question. So, Josh, how many of the 200 students have none of these courses? Well, in order to figure that out, I've got to subtract all the people in the courses. Add up every little subsection. Add up 17, 20, 15, 18, 16, 29, and 11. What do we get? Josh? 120. Well, what's the total in here? Is it? So 126 right here. Is that right? We've got, how many in science? We've got 80, 97, 108, 126. Do a little subtraction. What do we end up with? Go ahead, 74. A couple people. You could actually put the 74 right out here. It's not a part of any of those courses. One key rule for dealing with Venn diagrams is that if you're presented with a space, something is in it. The only reason that you see these overlaps is because whoever designed this Venn diagram wanted you to know that there's something in that space. It might be one element, or in this case, one person, but something's there. The fact that there's a box surrounding this and that there's empty space here means that something must be there, even if it was just one person instead of 74. You see space, something's in it. If this problem was designed where everyone took a course, then we wouldn't have the box around it, we would just have the three circles. So if there's space, if there's an overlap that's shown to you, like these footballs and this little shield shape that's directly in the center, you know that something's got to be in that space. Otherwise, the circles would be separate from each other. There wouldn't be any sort of overlap. So start with groups, work your way down to individual sets. Or in this case, up to the sets. Keep that in your Chapter 2 or Unit 2 file, whatever you have. Most of this chapter is going to go. We'll do a little bit of Venn diagram work or puzzle work. Then we'll take a look at some notes, most of which I will hand to you. We'll learn some new vocabulary. Let's move on. Very little computation in this chapter. If I write something, you write it down. If I underline something, circle something, you do the same thing. Circle the word conditional. We do a lot of vocabulary in this chapter, and for some reason, it's the very first word that people forget. Conditional is just our fancy way of saying we're dealing with an if-then statement. That's it. If you see the term conditional come up, we're just talking if-then statements. I'm going to redraw a few things so that you can see it a little bit better. We tend to use P and Q as our variables when we're dealing with conditional statements. But this isn't like your typical variable. These are variables for statements or clauses or groups of words. So P doesn't represent a number, it represents a set of words. Let's put P arrow Q over here. From now on, the international symbol for an if-then statement is going to be an arrow pointing to the right, surrounded by two clause variables. You could also say this, P implies Q. Or if P, then Q. You are eventually going to have to do a project sometime in the second, third, and fourth course. Your project could be something as simple as, why do we tend to use P and Q when we're discussing logic problems in geometry class? What's the historical significance of that? Why P and Q? Does it have something to do with the statement, mind your P's and Q's? And where does that statement come from? Yep. Any idea, Chloe? Huh? How does carrots mean Q, though? There's another story behind that phrase, right?
It means like when people are getting drunk and stuff, it would be pints of quarts and then it'd say minor.
I think so. I don't know for sure. I think it's pints and quarts, but that could be one of your projects during the second and third and fourth quarters, is to look that up and actually find out some sort of website or book as a source. In the second, third, and fourth quarter, you're going to write a proposal indicating what you'd like to do for your project. As long as I approve the proposal, you do your project, whether it's 1 page, 2 pages, whatever you want it to be. We'll get to that in the second quarter. For right now, realize that these letters stand for sentence clauses or phrases. In science class, you think of hypothesis probably as an educated guess. In our logic unit, we use hypothesis to represent the first part of the if-then statement. Underline, today is a green day, with 1 underline. Double underline, tomorrow is a blue day. This is considered the hypothesis. This is considered the conclusion. If and then are just considered the connecting words. So let's circle those. Whatever follows if, that's our hypothesis. Whatever follows then is our conclusion. We can write this a number of ways. We can write it with the word implies. We can write it with the words only if. Or we can put just if in the statement. The best way to take a look at this is just to do some practice questions. Let's take a look at these 4. Just circle all of the key phrases. Applies, if then, We'll start with that. The hypothesis for number 4 is right here. That's our normal phrase. If it rains, then the game will be canceled. If came first, that's the hypothesis. If you see the word implies, same deal. The first part is the hypothesis. If you see the words only if, it's still at the beginning. The only time the hypothesis is considered to be at the end is when the word if is totally by itself. So let's call that the exception. What you're going to find in this chapter, if you can find the exception to the rule, makes it a lot easier, because there's usually only one exception. If you can find the hypothesis, which we underline once, then the conclusion is whatever remains. So that's the conclusion, that's the conclusion, that's the conclusion. The only time the conclusion is considered to be first is when the word if is totally alone. Now, a lot of people ask, well, how come number 2 isn't like number 1? And I can't fully explain that. I'd have to have a little higher degree and maybe have a little more knowledge about English. A group of English majors and mathematics majors got together at some point and they decided that that's what that means. And you're going to find that that pops up a few times in the logic section. All of mathematics is man-made. So if you get enough people to agree on something, that's the way it is. How many degrees are in a circle? 360. Because a whole group of people, a whole mess of people, decided that that's the way it's going to be. And that's the only reason. So right now, take it for granted that this is correct, that I know what I'm talking about. And the only time where you have the hypothesis first is a case where the word if is all alone in the middle of your statement. We'll come back to that and I'll explain it. I'll show you a couple websites that explain it. And they come from English websites, not mathematics. It has to do with the wording. That's how your test is going to start. Just picking out hypothesis and conclusion from various statements. You think you can do that? You're going to find that this chapter, if you can read, can everybody read in here? It's not that bad because there's not a whole lot of mathematics in terms of calculation and computation. And this is the bare bones of everything about logic. We don't get into this too deep. If you take a discrete math course later on or a higher level geometry course, you'll really get into the logic. You might want to do that as your project in the second, third, and fourth quarter. You might want to take it to the next step. We don't cover De Morgan's laws. Maybe you would want to do a little research and tell me what De Morgan's laws are. It's the next step after what we're talking about today. We just don't get to it this year. Page 2. This is the meat and potatoes of what you need this year. Let's write out this phrase up here. If you see an arrow, what does that mean? What kind of phrase are we talking about? Raise your hand, give me Chloe. Conditional statement. That's the term that I want you to start using. Yes, it's an if-then statement, but it's also called a conditional statement. So let's write it out. If a number is divisible by 4, then the number is even. If you can make an abbreviation or a shortening of a word, go ahead. If I do it, you're allowed to do it. Let's shortened divisible to div. You have to have something in front of you. So we're being handed that phrase. Right now, we don't care if this is true or not. We're just manipulating the statements. We'll worry about whether things are true and false a little bit later on. Converse. When you see the word converse, I want you thinking switch position. And you can see over here, we've switched our variables. Now the P is second, the Q is first. What does the arrow mean? What kind of statement? Conditional. Do I still use if and then? Yes. Those don't switch. If remains first, then remains second. Don't switch the connecting words. Only switch the phrases themselves. So if a number is even, then the number is divisible by 4. If I use an abbreviation or a symbol, you're allowed to use it. Use the number symbol. It's okay to make little changes to articles and verb tenses, as long as you're maintaining the same meaning to each of your phrases. You'll notice I changed little things like a and the. That's okay. If I want to change a verb tense, that's all right. Just make sure that the general meaning of each of your phrases is the same. Inverse. Circle beginning of that word. What do we call little attachment to the front of a word? Prefix? If I say that Kevin is incompetent, what am I really saying? I'm saying he is blank competent. What word would you stick in there? Not. That's what I want you thinking right here. Anytime you see the word in, think how incompetent Kevin is. Put the not there. We don't tend to use the word not to define this. We use the word negate. Same thing. Not is what we tend to use to negate something, but sometimes we're taking the word not out of a phrase. What if the word not is already in a phrase and we want to negate it? Generally, you're trying to get an opposite meaning. So there's going to be many ways that we can write down the negation. Sometimes you can put down the word not, sometimes you can put down an opposite idea. Notice, we did not move the positioning. P is still first, Q is still first, but what's in front of them? What do you see next to the actual letters? What would you call that? I don't know if there's a mathematical term for that, but what do you call that in Spanish class? A tilde? I'm going to refer to it as a tilde, or a negation symbol. If somebody knows of a math phrase that corresponds to that, let me know. If still goes first, but now we're putting in the word not into the phrase. If a number is not divisible by 4, then the number is not even. Once again, I really don't care about whether these new phrases or old phrases are true or not. I'm just manipulating the phrases. Where we see mistakes, people don't negate both parts. In order for this to be an inverse statement, you have to negate the beginning and you have to negate the end. Contrapositive. I want you thinking both. We are going to switch and negate. Notice Q is first, and it has a tilde in front of it, or a negation symbol. P is second. It also has a negation symbol in front of it. They've switched positions, and we've negated them. If a number is not even, then the number is not divisible by 4. Just some vocabulary and some manipulation. Underline the word counterexample. Here's where we're starting to actually care whether the statements are true or false. An example that proves the statement is false. In order to prove that something's false, you need only one counterexample. It doesn't have to be a group of examples. Just one makes it false. Right now, this is asking you to provide a counterexample. I'm not interested right now. We'll get to that a little bit later down here. Biconditional. Biconditional is what we associate with the term if and only if. And it looks like this. You might see double arrows with a thick line in between. You might see it like this, where you have a thin line in between. As long as you have two arrows, one in each direction, we're talking about a biconditional. Circle these two. Instead of writing a conditional phrase and then its converse and having two phrases, we just combine them into one. You know biconditionals by the term definition. You've been using biconditionals your whole life. We're just giving definitions a new name. Definitions are biconditionals. The example that's given, an angle is a right angle if and only if its measure is 90 degrees. If you can read the phrase backwards and forwards and it makes sense both ways, you've got yourself a definition, and we call it a biconditional. An angle is a right angle if its measure is 90. How about if something's measuring 90? Is it a right angle? It's a biconditional, it's a definition. It works both directions. Now let's do some examples where we actually care whether it's true or false. Tell whether the given conditional is true or false. If x is less than 4, then x is negative. Raise your hand. Tell me if it's true or false, but then give me a counterexample. Ryan? It's false. What would be your counterexample? All right. So my counterexample would be x equal to 3. We want one case that would make the beginning false. So let's underline, what do we call the first part of an if-then statement? Hypothesis. So we're looking to make the hypothesis true, but it leads to a false outcome. Is x equal to 3 also less than 4? That's true. But is x equal to 3 negative? No. That's our counterexample. Your counterexample might be a sentence. It might be a paragraph. In this case, it's just stating a number. Every problem is going to be a little bit different. But the idea is to make the beginning true and the conclusion false. Hypothesis true, conclusion false. We're supposed to write the converse, inverse, and contrapositive of the original statement. Remember, we can move things around, we can change verb tenses, we can make little changes. Here, we don't have to do too much. We can just manipulate what we've got in front of us. Arrow means if then, so I wrote if then automatically. Write down the word switch. What corresponds to us thinking of the word switch? Is that converse, inverse, or contrapositive? Boomer? Converse. Write that down. All we're doing is switching, and we have x is negative. Then x is less than 4. So, Umer, is this new statement true or false? Let's see. If x is negative, true. Any real number we choose is also going to be less than 4, as long as it's negative. Try out some numbers. Negative 11. Is negative 11 less than 4? Yes. Any negative number I choose is going to be less than 4. That statement's always going to be true. How about this? Looks like I'm negating. I see the negation symbols. I see the little tildes. The position hasn't switched. What does that indicate? What kind of phrase are we dealing with? Inverse. Remember to negate both parts of the if-then statement. If, I've got then, if x is, what would be the opposite idea of x less than 4? Kevin?
I'll put the exclamation mark x is less than 4.
Exclamation mark.
And we use that in computer math. Like if it's not equal to or something.
Let's use a different symbol that we're more used to here. I know what you're talking about. What language is that in usually?
We're doing like Java right now, but using Java.
Java? Peyton? Greater than wouldn't be enough, because that still doesn't account for when x is equal to 4. So if we're doing the opposite idea, you have to include everything that's not less than 4. Kyle?
X is greater than
You got to have greater than or equal to. You've got to include everything that is the opposite idea to what you have. Same idea here. We want to negate x is negative. You can't just write down x is positive, because what aren't we including? 0. So how can I include 0 and positive in one statement? What symbol would I use to include 0 and positive numbers? Chloe? If x is a whole number, that doesn't include decimals and fractions. She's close, yes?
Just
All right, he just said x is not negative. That's the easy way out, and that would be true. But how about if we do this? Isn't that the same as saying x is not negative? X is 0 or above. And what he said was fine. I could have said, if x is not less than 4, then x is not negative. But we're in math class, so let's use some inequalities. Is this true? If x is greater than or equal to 4, then x is greater than or equal to 0. Try out some numbers. I'm hearing yes from everybody, so I'm going to write true. Well, let's test it. Is 4 greater than or equal to 4? Is 4 greater than or equal to 0? You've got larger numbers here than 0 to start with, so they're definitely going to be larger than 0 over here. And the last one, we are switching and we are negating. Switch and negate. What do we call this? Contrapositive. Notice in all of these, we did not move around the word if or the word then. They stay in their respective spots. Now I can just really look at the one right above it. I already negated here, I just have to add in the switch. So I can put x greater than 0, x greater than equal to 4. X greater than or equal to 0, x greater than or equal to 4. Is that true? Try it. No? Can you give me a counterexample? All right, let's try out x equals 1. This was our counterexample. Here's another counterexample. If I put a 1 here, does it make this true? Is 1 greater than or equal to 0? Yes, we want the first part to be true. Is 1 greater than or equal to 4? No. So we got a true leading to a false. That makes the entire statement false. We only need one counterexample. There's many, but we only need one. Is that it for that page? You now know the basics of inverse, converse, contrapositive. You've learned some new vocabulary. You know the basic building blocks of the entire chapter now. When I said that Kevin was incompetent, that was, everybody realizes, sorry, so he got 100 on every single section of the test. Nice job. And I think there were a couple people who had hundreds all the way through the test. While I'm passing out the test, Elizabeth is going to give everybody a correction sheet. You're going to do corrections on your test, which means correct answers and an explanation of what you did wrong. You're going to tell me in complete sentences what it is that you did wrong. Did you not memorize a formula? Did you make a mistake doing an algebra equation? Whatever it is, you explain it to me. If you can explain it to me, chances are you're not going to make the same mistake twice. This counts as a separate homework assignment. It counts just as much as this algebra assignment. So if you didn't do so well on your algebra assignment, now you have something that you can average in with it to help out that grade.